So, have you ever just stopped and wondered, how did all of this begin? I don't just mean us, I mean the actual ground we're standing on. Today, we're going to dive into the incredible 4.5 billion years story of how our Earth came to be, from, just a swirling cloud of dust to the amazing world we call home.
We all know that one, right? It's funny, that simple feeling of wonder we get when we look up at the stars, it's something every single one of us feels. It's this universal thing that connects us. And it starts when we're just kids.
And that wonder, well, it leads to one of the biggest questions you can possibly ask. Before any of us, before all of human history, even before the Earth itself was here, how did it all start? That's the huge mystery we are going to try and unravel together in this explainer.
Okay, so to get to the answer, we first have to start with the question itself. And believe me, it's a question humanity has been wrestling with for a very, very long time.
This isn't some new age curiosity. We're talking centuries ago, long before we had any of our fancy, powerful telescopes. Some of the greatest thinkers in history were staring up at that exact same night sky, trying to piece together the incredible puzzle of where we came from.
So what was the first big scientific swing at this question? Well, it all kicked off with a simple but absolutely gigantic cloud. And this idea got a name, the nebular hypothesis. Now, nebular sounds complicated, but it's really just a word for a massive cloud of gas and dust hanging out in space. The theory was that our entire solar system, the planets, the moons, everything, was born from a cloud just like this, one that was swirling around a brand new baby sun. And this wasn't just some random guess. It came from some truly legendary minds. The philosopher Immanuel Kant was actually the first to float the idea. But then it was the brilliant French mathematician Laplace who really tightened it up and gave it a solid mathematical backbone way back in 1796.
So, the original theory was actually pretty elegant and straightforward. Step 1, you've got a young sun and it's slowly spinning. Step 2, it's surrounded by this huge cloud of, well, stuff. And step 3, over a long, long time, that stuff starts to clump together and voila, you get planets. Simple, right?
Now here's the wild part. For more than 150 years, this was the best explanation science had. That just goes to show you how powerful a good idea can be, even if you don't have all the details worked out yet. It was our #1 clue all the way up until the middle of the 20th century.
But of course, that's what science is all about, right? Building on what came before. And in the 20th century, a new generation of scientists decided to take a much closer look at that big old cloud. So in the 1950s, you have these two scientists, Otto Schmidt over in Russia and Carl Weizsäcker in Germany. And working independently, they both revisited that old nebular hypothesis. And they added some absolutely crucial new details that were about to change everything. And this is where the picture really gets sharp. That vague cloud of material, it's now called a solar nebula. And they figured out it was made mostly of hydrogen and helium, the most common stuff in the whole universe. But here's the real game changer. They figured out how it all happened. All the friction and collisions between particles in the cloud would cause it to flatten out into a spinning disk. The how wasn't a mystery anymore. It was just physics in action. And that led them to the key ingredient, accretion. You can think of it like a cosmic snowball effect. Tiny little dust particles bump into each other and stick. Then those clumps hit other clumps. Over millions of years, they grow from pebbles to boulders to these huge things called planetesimals, basically the building blocks for planets like our own. This one concept, accretion, explained how you could get an entire solar system from just a bunch of dust. Pretty amazing.
So, with a solid theory for how planets get made, the scientific community had this powerful new tool. But solving the mystery of Earth's origin immediately created an even bigger question, a much bigger question. Because if they could figure out how our solar system was born, well, couldn't the same rules apply everywhere else? Suddenly, the camera zoomed way, way out, from just our little planetary neighborhood to the entire universe.
Yeah, the whole focus just shifted dramatically. The scientific world turned its attention from the local mystery of our solar system to the ultimate mystery of the whole cosmos. As they put it, they began to take up the problems of origin of universe rather than that of just the Earth or the planets.
And that's where this part of the story leaves us. The journey to understand our own home led us straight to questioning the origin of literally everything we see in the night sky. So the next time you look up at those twinkling stars, just remember, you're not just seeing little lights. You're looking at clues to a story that's even bigger than our own.
Have you ever just looked up at the night sky and wondered, where did all of this come from? You know, the stars, the galaxies, you, me, everything. It's got to be one of the biggest questions we could possibly ask.
Well, today, we're going to try and tackle that exact question. We're diving deep into the origin story of our universe, looking at the best scientific story we have, and it all starts with one single, powerful idea. And that idea is, of course, the Big Bang Theory. Now, I'm sure you've heard the name, but what does it really mean? Well, check out that other name for it, the expanding universe hypothesis. That right there, that idea of expansion, that's our very first clue. To figure out how it all began, we actually have to start with what we can see happening right this very second. And that part of the story kicks off about 100 years ago. So, back in 1920, an astronomer named Edwin Hubble made a discovery that changed everything. He found solid evidence that galaxies aren't just floating out there, they're all moving away from each other. The entire universe is actually getting bigger.
So how do you even picture that? Well, the classic way to think about it is with a balloon. Imagine you take a balloon and draw a bunch of dots on it. Each dot is a galaxy. Now start blowing it up. What happens? Every dot gets farther away from every other dot, right? Not because the dots are crawling around on the surface, but because the balloon itself, the space, is stretching.
Okay, but here's where we have to be really clear, because this is where the analogy kind of breaks down a bit. It's not the galaxies themselves that are expanding. Our Milky Way isn't stretching out. It's the literal space between the galaxies that is expanding. The very fabric of reality is growing.
All right, so if we know that everything is moving apart right now, that leads to a really obvious logical question. What happens if we run the film backward?
I mean, think about it. If all the galaxies are flying away from each other today, then yesterday they had to be closer together. And the day before that, they were even closer. If you just keep rewinding and rewinding, you eventually get to a single moment when everything, all the stuff, all the energy in the entire universe was crammed together into one single spot. And what was that spot like? Well, scientists sometimes call it a singular atom, or a singularity. And this is where things get truly wild. We're talking about a point with a volume so small it's basically zero, but with a temperature and a density that were basically infinite. All of existence, squeezed into a point so extreme that our laws of physics just don't apply.
And when was this? All the evidence we have points to one date, about 13.7 billion years ago. That is how old our universe is.
So at that moment, 13.7 billion years in the past, this tiny, infinitely dense ball exploded with unimaginable violence. And this wasn't an explosion happening in space, it was the explosion of space itself. That event, that was the Big Bang.
So, the explosion happens, then what? Well, the moments right after the Big Bang were maybe the most chaotic and important in the history of, well, anything. In just the first tiny fractions of a second, the universe went through this period of insane, super fast expansion. And as it ballooned outward, all that pure energy started to cool and convert into matter. In fact, within just the first 3 minutes, the conditions were finally right for the very first atoms to start forming.
Now, after that initial crazy burst, the expansion did slow down a bit, but, and this is key, it never stopped. It is still expanding right now, this very second, carrying all of those galaxies farther and farther apart.
For a pretty long time, the early universe was this super hot, dense, foggy soup of particles. You wouldn't have been able to see your hand in front of your face because light couldn't travel anywhere without immediately getting bounced around. But that was all about to change.
It took another 300,000 years for the next big milestone. Now, that sounds like a long time to us, but on a cosmic scale, it's just the blink of an eye. So what happened in that time? Well, as the universe kept getting bigger, it also got cooler. And once the temperature dropped down to about 4,500 Kelvin, something amazing happened. Stable atoms could finally form. This was an absolute game changer. See, once those atoms formed, they basically cleared up all that cosmic fog. For the very first time, particles of light, photons, could finally travel across space without getting scattered. The universe, for all intents and purposes, became transparent. This was the moment light was finally set free to travel across the cosmos. Now, it's really important to remember that huge scientific ideas like this are almost always debated. For a long time, the Big Bang wasn't the only game in town. There was another major theory competing for the top spot. So on one hand, you've got the expanding universe model we've been talking about, which says the universe had a definite beginning and has been changing ever since. But on the other hand, there was the steady states theory. This idea, championed by an astronomer named Hoyle, suggested that the universe has always existed, and it's always looked more or less the same. No beginning, no end.
But as scientists gathered more and more data, things like Hubble's discovery of galaxies moving apart, the evidence just kept piling up, and it overwhelmingly pointed to an expanding universe with a beginning. So today, the vast majority of the scientific community agrees that the Big Bang model is the one that best fits the facts.
So let's do a super quick recap of this incredible story. The universe kicks off 13.7 billion years ago from a single infinitely dense point. It's been expanding ever since, a discovery we owe to Edwin Hubble. Within just the first 3 minutes, the first atom started to pop into existence. And after 300,000 years, the universe cooled enough to become transparent, letting light travel freely for the first time.
And all of that leaves us with one last, truly mind-bending question. If the universe, which is by definition everything, is constantly getting bigger, what is it expanding into? That's something to think about the next time you look up at the stars.
Have you ever just looked up at the night sky and really wondered, where did all that come from? I mean, everything. Well, today we're going to go on a little cosmic journey. We're going to trace the origin of a star all the way back to the very beginning of time itself.
It's one of those questions that just feels impossibly big, right? We see them every single night, these tiny glittering dots. But what are they really? What's the cosmic recipe that actually cooks up a star in the middle of all that empty space?
You know, the answer is actually kind of amazing and surprisingly simple. It doesn't start with some giant explosion. It starts with leftovers. See, the universe wasn't perfectly smooth when it began, and that simple fact, that little bit of cosmic lumpiness, is the secret ingredient for literally everything that came after.
Okay, so let's rewind the clock. Way back. We're talking about the conditions right after the Big Bang, where the seeds for every single star and galaxy were first planted.
So here's the basic idea. Just imagine a fog that isn't perfectly uniform. It's got thicker patches and thinner patches. That was the early universe. The slightly thicker spots had just a tiny bit more gravity. And that's all it took. Gravity started doing its thing, pulling more and more stuff into these denser areas, creating this cosmic snowball effect. Now, as those little gravitational hotspots just kept pulling in more and more material over millions of years, the first huge structures started to form. We're talking about entire galaxies.
And this is where that chain reaction really kicks into high gear. Those tiny little differences in density at the beginning, those were the blueprints. And gravity? Well, gravity was the construction worker, taking those plans and building these enormous, sprawling cities of stars that we call galaxies.
And the scale here is, well, it's just mind-boggling. A typical galaxy can be anywhere from 80,000 to 150,000 light-years across. We'll get to what a light-year is in just a second, but for now, just try to wrap your head around that. These aren't just little clusters of stars. They are massive islands floating in a cosmic ocean.
So, we've gone from the early universe to a whole galaxy. Now, let's zoom in again. Let's go deep inside one of these galaxies to find the exact spots where new stars are being born right now. We're heading into what astronomers call a stellar nursery.
And this stellar nursery has a name, a nebula. All it is, really, is a gigantic cloud made almost entirely of hydrogen gas, which is, the most basic building block in the entire universe. It's inside these enormous, beautiful clouds that the real magic of star birth actually begins.
All right, we've gathered all our ingredients. We've got our lumpy early universe, we've got the force of gravity, and we've got a massive cloud of hydrogen. So now, let's watch how they all come together to create a brand new star.
It's actually a really logical process. Gravity pulls all this hydrogen gas together into that giant nebula. But inside that huge cloud, little clumps start to form, pulling in even more gas, getting denser and hotter. And eventually, one of these clumps gets so incredibly dense and hot that a whole new process kicks in, nuclear fusion. The pressure is so intense that hydrogen atoms literally fuse together, releasing an unbelievable amount of energy. And in that brilliant flash, a star is born.
And to bring this a little closer to home, our own sun is thought to have formed in this exact same way about 5 to 6 billion years ago. We are literally living in the light of a star that was born from an ancient cosmic cloud.
Okay, so I've been throwing that term light year around. To really get a feel for the size of a galaxy, we have to understand this cosmic measuring stick. So what exactly is a light year?
So the most important thing to get straight is this. Even though it has the word year in it, a light year is a measure of distance, not time. It's simply the distance a beam of light can travel in one single year. And as you probably know, light is, well, it's incredibly fast.
How fast are we talking? 300,000 kilometers every single second. That's so fast it could zip around the entire Earth more than 7 times in the blink of an eye. It's just absurdly fast. So if you let that beam of light travel for one full year, it covers a staggering 9.5 trillion kilometers. That is one light year. There's really no other way to measure the insane distances between stars and across galaxies.
And to put that into perspective, check this out. The light from our own sun takes about 8 minutes to get to us here on Earth. That means when you look up at the sun, you're not seeing it as it is right now. You're seeing it as it was 8 minutes ago. So when you look at a star that's 1 light year away, you're actually seeing it as it was a full year in the past. You're looking back in time. Which brings us right back full circle to our main idea. Everything we've talked about, the nebulae, the stars, the crazy distances between them, it all goes back to one simple fact. The early universe wasn't perfectly smooth. That initial cosmic lumpiness, it's the mother of all creation.
So let's just end on this thought. Stars are born from this recycled cosmic dust. They live for billions of years, and when they die, they scatter new, heavier elements back out into space. Which leaves us with a final, kind of beautiful question. If we are literally made of stardust, what will the dust that we leave behind become next in this grand cosmic cycle?
All right, today we're diving into one of the biggest origin stories you can possibly imagine. How does a planet, actually become a planet? We're going to go from cosmic dust all the way to a finished world, and we're breaking down exactly how it all happens.
It's a huge question, right? When you look up at the night sky, or heck, even just look down at the ground beneath your feet, have you ever really stopped to wonder how all of this got here? Well, it's not magic. It turns out it's this fascinating, step-by-step cosmic process that we're about to walk through together. So, let's start at the beginning. Our story kicks off in what looks like the emptiest place imaginable, a huge, beautiful cloud of gas and dust that we call a nebula. This is stage 1. Now, a nebula isn't perfectly smooth. It's actually kind of clumpy. The whole process really gets going inside one of those thicker parts, a localized lump of gas. You can think of this as the raw material, the cosmic nursery, where a new star and its future planets are about to be born. So how does that simple lump turn into anything? Well, the answer is the universe's ultimate sculptor, gravity. It starts pulling all that gas and dust inward, packing it tighter and tighter, which forms this dense, hot core at the center. But it doesn't just collapse into a ball. As it shrinks, it starts to spin faster and faster, which flattens all the surrounding material into this enormous rotating disk. And this disk, this is our construction zone.
Okay, so we've got our spinning disk. Now we're moving into the next phase, which is a lot more chaotic. It's time to make the actual building blocks for the worlds to come.
Inside that massive spinning disk, things finally start to cool off a bit. Gas condenses into tiny, solid particles, almost like cosmic snowflakes. And these little particles, they start to bump into each other and stick together, clumping up into what the slide calls small, rounded objects. These are the very first seeds of a brand new world.
And these small, rounded objects have a pretty awesome name: planetesimals. Really, all that means is you've got a huge swarm of these smaller cosmic bodies. Just try to imagine billions of these tiny pebbles all circling that new core together. So how do you get from a bunch of pebbles to an actual planet? Well, 2 things are happening at once: collision and gravity. You can think of it like a cosmic demolition derby, where instead of exploding, the cars just kind of fuse together after they crash. These planetesimals are constantly bumping into each other, and gravity helps them merge and stick. It's kind of like rolling a snowball down a hill. It just keeps picking up more snow and getting bigger and bigger. That is exactly what's happening here. This wild, chaotic process of crashing and growing leads us straight into the grand finale of our story, the actual birth of a fully fledged planet. The scientific name for this final act is accretion. It's just a fancy way of saying it's the process where all those countless planetesimals finally come together.
The bigger ones, which now have stronger gravity, they start to act like cosmic vacuum cleaners. They just sweep up everything in their path, clearing out their orbits and growing into the giants of this new solar system. And this, right here, perfectly sums up the transformation. You go from a completely chaotic swarm, a massive number of smaller bodies, to a much more organized system with just a few very large bodies. Through accretion, all that chaos finally gives way to order.
So here's the thing that's so incredible to think about. This isn't some abstract story that happened billions of light years away. This is our story. About 4.5 billion years ago, this is exactly what happened right here. The very ground we're standing on is made from the leftovers of those ancient colliding planetismals. This cosmic origin story, it's our own autobiography.
So, we've traced the entire journey, from a simple lump of gas to a world. It's the story of Earth, and that leaves us with this incredible, mind-bending question. As we stand here on our finished world, how many other stories just like ours are only just beginning, right now, out there among the stars?
Have you ever wondered what our planet was like at the very beginning? I mean, 4.6 billion years ago? Well, I can tell you it was nothing like the world we know. Today, we're going on an epic journey back in time to see how Earth went from a fiery, hostile ball of rock to the beautiful blue and green home we love.
So let's just really try to picture this. What did our planet actually look like at its birth? I want you to forget everything you know. The oceans, the continents, the clouds. Instead, try to imagine a chaotic, violent, and completely alien world. It's almost unimaginable. I mean, the contrast here is just staggering, right? On one side, you've got early Earth, molten, constantly being hit by asteroids, with a thin little atmosphere of hydrogen and helium. And on the other, you have today's vibrant, living planet. This entire explainer is about that incredible journey from that to this. Okay, so our story begins in total chaos. Picture a barren rock, intensely hot, and under constant bombardment from whatever was left over from the formation of our solar system. The atmosphere, if you could even call it that, was just this thin, wispy layer of hydrogen and helium. Totally useless, not to mention toxic for us. So how in the world does a chaotic ball of rock start to get organized? Well, the very first crucial step didn't happen on the surface at all. It happened deep inside. The planet had to literally sort itself out, and that process would set the stage for everything that followed. You see, early on, there was just so much heat from its formation, from radioactive decay, from all those asteroid impacts, that the entire planet was basically a giant glowing sphere of molten rock. And that liquid state was the key, because it meant everything inside was free to move around. This planetary sorting process has a name. It's called differentiation. And honestly, the best way to think about it is like a big bottle of salad dressing. You shake it up, but if you let it sit, gravity takes over. The heavier stuff sinks to the bottom, and the lighter oil floats to the top. The exact same thing happened to our entire planet, just on a massive scale. So here's how it all went down. As the planet heated up, everything inside became mobile. Gravity just took over from there. The heaviest elements, things like iron and nickel, started this slow-motion dive toward the center, forming the planet's core. And at the same time, all the lighter materials, the stuff that makes up rocks, floated up toward the top, where they eventually cooled and hardened into the crust we live on today. And the end result was a planet with a brand new, organized internal structure. You've got the thin outer crust, the huge mantle in the middle, and then the super dense metallic core. Now, this layering wasn't just for looks. It created a dynamic engine. For instance, the liquid outer core, spinning around, gives us our magnetic field, which acts like a shield, protecting us from harmful solar radiation. This structure was absolutely foundational. All right, so with solid ground beneath our feet and a magnetic shield in place, Earth was ready for its next big act, creating an atmosphere and its oceans. And this wasn't just a one-and-done event. It was a dramatic, multi-stage evolution. You can really think of the story of our air in 3 key phases. First, Earth had to get rid of its original, useless atmosphere. Second, it had to create a whole new one from the inside out. And finally, and this is the most amazing part, life itself would show up and completely change it all over again. That first atmosphere of light gases, yeah, it didn't stick around for long. The young sun was a wild and powerful star, and its intense solar winds basically sandblasted Earth and the other rocky planets, just stripping away that initial blanket of gas and leaving the planet completely bare. So, with atmosphere number 1 gone, how did Earth get a second chance?
The answer literally erupted from within. Through a process we call degassing, the planet's super hot interior just vented everything. I mean, imagine the entire planet covered in volcanoes, all erupting nonstop for millions of years, just belching out all the gases that had been trapped inside since the planet formed. And this new atmosphere was, well, it was intense. It was thick with water vapor, tons of carbon dioxide, and nitrogen. A real cocktail of volcanic gases. But look closely at what's missing. There was practically no free oxygen. This was still a toxic, completely unbreathable world for anything like us. So all that water vapor that the volcanoes pumped out couldn't just stay in the air forever. As the surface of the planet finally slowly began to cool down, all that steam condensed into clouds, and this kicked off a rainstorm of truly epic proportions. We're talking a torrential downpour that might have lasted for millions of years, filling up every basin, every crater, every depression, and giving birth to our planet's very first oceans. 4 billion years ago. That's how ancient our oceans are. They formed within the first 500 million years of Earth's existence. But these weren't just big pools of water. No, they were these chemical-rich cauldrons, protected from the harsh radiation of the sun. And it was right here, in these new oceans, that the stage was set for the next, and maybe the most profound, transformation of them all. Because once you have oceans, you can have life. And when life arrived on Earth, it wasn't just a passive passenger. Oh no, life was about to become the single most powerful force for change that the planet had ever seen. What's really mind-bending when you look at this timeline is just the sheer scale. Look at the gaps. Life pops up pretty quickly after the oceans form, which is amazing. But then for nearly 2 billion years, it's just hanging out before it makes its biggest move, the moment it starts to completely re-engineer the atmosphere. For a huge stretch of geologic time, life existed only under the waves. The land was still a sterile, irradiated wasteland. The oceans were a safe harbor, and it was in this underwater world that a revolutionary new trick evolved: photosynthesis. Life literally learned how to eat sunlight. And here's the game-changing twist. As a waste product, these new life forms started pumping out oxygen. But for hundreds of millions of years, none of it even made it into the air. You see, oxygen was poison to most early life, and it was immediately soaked up by iron dissolved in the oceans, which then rusted and sank to the seafloor. Only when the oceans were totally saturated, when they literally couldn't absorb one more molecule, could oxygen finally start to escape and flood the atmosphere for the very first time. And that event, which scientists call the Great Oxygenation Event, is what finally created the world we recognize. It paved the way for bigger, more complex life and literally changed the color of our planet, from a dusty, reddish-brown to the beautiful blue and green world we see from space. When you really trace the steps, it's just this unbelievable chain of events. A molten ball of rock sorts itself out from the inside, creating a protective shield. Volcanoes then breathe out a new atmosphere and fill the oceans with water. Then, tiny life forms appear in that water and over billions of years terraform the entire planet just by breathing. Each step made the next one possible. If there's one constant in Earth's incredibly long story, it's change. Our planet isn't some static museum piece. It's a living, dynamic system that has reinvented itself again and again. It really makes you wonder, after a 4.6 billion year journey, what's next for our ever-changing home?
All right, let's get into it. Today we're tackling one of the biggest questions out there. Where did all of this come from? Not just people, I mean all life. We're going to unpack the incredible story of how a dead rock, just spinning in space, turned into the living, breathing world we call home.
So this is the big one, right? How does a planet with, nothing on it suddenly spring to life? You start with just rocks, water, and gas. And somehow, out of that primordial soup, life emerges. It sounds completely impossible, almost like magic. But it turns out, science has a pretty mind-blowing explanation. So to really get how life started, we've got to go back, way back. We need to picture the stage where this all happened, because the Earth, billions of years ago, was a totally different planet.
Yeah, not conducive. That has to be the understatement of the millennium. We're talking about a world that was just hostile. A toxic atmosphere, volcanoes erupting all the time, constantly being blasted by radiation. It was pretty much the last place in the universe you'd expect to find life getting its start.
So how in the world did anything survive, let alone begin, in that kind of chaos? Well, the answer isn't some magical bolt of lightning or a single miraculous event. It's actually something much more fundamental, something baked into the laws of the universe. And this is the absolute key to the whole thing. The mystery of the origin of life isn't really about biology, it's about chemistry. It's all about having the right ingredients in the right conditions, starting a chain reaction that would literally change the face of the planet. So what's in this recipe?
Okay, so you can break down this huge, planet-altering chemical reaction into 3 basic steps. Step 1, you need to create the building blocks of life, complex organic molecules, from all this simpler stuff that was just lying around. Step 2, those molecules had to somehow organize themselves to assemble into more complex structures. And step 3, the real game changer. Those structures had to figure out how to make copies of themselves.
And when that final step happens, when a collection of molecules finally learns how to duplicate itself, that's when something truly profound takes place. It's maybe the most amazing transformation we know of. This really gets to the core of it. Scientifically, that's the moment non-living matter becomes a living substance. The defining feature isn't breathing or thinking, not at this early stage. It's just that simple, but incredibly powerful ability to self-replicate. That's the spark of life.
Okay, it's a fantastic theory, right? Life is just one big chemical process. But this all supposedly happened in the super deep past. So how on earth could we possibly know if it's true? I mean, where's the actual proof?
Well, luckily for us, the Earth basically kept a diary. The entire history is written down, and if you know how to read the language, the story of early life is waiting right there for us, written in stone, literally. And that diary, of course, is the fossil record. Fossils are these incredible little time capsules, right? They're snapshots from the past that tell us not only that life existed, but also what it looked like and when it was around. This is our hard evidence.
And you better believe we found them. Not, huge T-Rex bones, but something way, way older. Buried deep inside ancient rocks, scientists have found the fossilized remains of tiny, microscopic structures. And the amazing part? They look a whole lot like a simple organism we still have today, blue-green algae. This is the smoking gun.
So we've got the evidence. We know how it could have happened, and we have fossils to prove it was happening. Now we can finally start putting some dates on this thing. Let's see where these events fall on a timeline. So check this out. Our oldest direct fossil evidence, those little algae-like structures, they're about 3 billion years old, which is just insane. But that's just the first physical proof we've managed to find. Based on chemical models, scientists figure the whole process probably kicked off even earlier, maybe around 3.8 billion years ago.
Seriously, just take a second and look at that number. 3,800 million years. Try to really wrap your head around that. It's a timescale that's almost impossible to really feel.
So when you put it all together, our best scientific understanding points to this. Life's chemical journey started almost 4 billion years ago, on a planet that we wouldn't even recognize today. And from that simple, chemical beginning, every single living thing you've ever seen eventually emerged. And that, of course, leaves us with one last, truly mind-bending thought. If life on Earth wasn't some 1 in a trillion miracle, but just the natural result of chemistry and physics doing their thing, well, what does that mean when we look up at the countless other planets in our galaxy? If it happened here, why not somewhere else?